this lecture, we're going to look at some of the properties of graphs. When I say graphs, I mean undirected graphs like this. Okay. So an undirected graph is connected if for each pair of nodes, or vertices, there exists a series of edges joining them together. So let's have a look here. So let's take a connected graph over here and some kind of a disconnected graph over here. So let's call this A, B, C, and let's say edges here to here and here to here, and sure we'll throw in a loop there. And a disconnected one, let's join these two, let's have a loop, let's join this to this, and let's make a little triangle there like that. Okay. And call this A, B, C, D, E. Okay, maybe I'll call it F as a better name. Okay, let's maybe name the edges. So edge 1, edge 2, and this loop is edge 3. Let's call in this graph edge 1, edge 2, edge 3, edge 4, edge 5. So as you can see, if you pick any pair of elements here, there is a walk between them, a series of edges. So for example, if you pick A and B, edge 1. If you pick A and C, edge 1, edge 2. If you pick B and C, edge 2. Okay? Whereas over here, if you pick B and C, there is no series of edges that can get you from B to C. So this graph is connected, and this graph is not connected or disconnected. And it's got two what are called components. A good question now, which is how can we tell whether a graph is connected or not? Okay, now this task is another collaborative task, let's see, which you can try and do on your own, but ideally it's meant for groups of maybe 2 or 3 students or possibly 4, but obviously we don't have groups, so this is a little bit messed up. So I'll probably pause it and invite you to try and complete this, and then we'll see what I come up with. We might come up with different things. Okay, so given an undirected graph, describe an algorithm, a series of tasks that determines whether or not the graph is connected. Here are some graphs to consider to help you find such an algorithm. So first of all, maybe we might start labeling some of the vertices. So V1, V2, V3, V4, V5, V6. So the question is this graph connected? Now, one of the things is, let's be clear here, you can't get from V1 to V4 via this bit here. There's an edge from V4 to V5, V5 to V6, and V6 to V4. There's no way that you can get to V1. So this is, in terms of connected or disconnected, this is disconnected. Whereas this one is connected, this one is connected, and this one is disconnected, because you can't get from here to here. If you try, you won't be able to do it. So the question is to come up with an algorithm. Now, one of the things you could do might be related to how you write down the definition. So if I write this as graph 1, and if I name the edges, say, I'm just going to write the numbers, but there'll be little indices. So edge 1, edge 2, edge 3, edge 4, edge 5, edge 6. So maybe just for a little bit of revision, we'll write down the set of vertices and edges of graph 1. So graph 1 is equal to a set of vertices and a set of edges, where the set of vertices is vertex. We got 1, 2, and it's not 2 graphs, it's to be considered 1. You could say this is 4 components of an undirected graph. That's not actually my intention. My intention is that it's 4 different graphs. So V1, V2, V3, V4, V5, V6, set of vertices and the edges. Now actually I've written down these like edge 1, edge 2, but actually I'm going to go back to using the 2 element subsets instead. So we have an edge between V1 and V2. We have an edge between V2 and V3. We have an edge between V3 and V1. we have an edge between v4 and v5, an edge between v5 and v6, and finally an edge between v6 and v4. So like the thing is about, you know, putting an algorithm, a series of tasks to determine whether a graph is connected or not. The question, like, how much functionality have you got? Are you able to kind of play around with the graph, or do you just have this data here? Now, if you've just got this data here, it's going to be far more difficult to actually describe the algorithm. But I'll tell you how I would figure out if something. Like, remember, when you're programming, you've got to think. Computer is very, very dumb. You have to tell it everything, and you can maybe come up with some kind of an algorithm, compare it what I do here. So the idea behind the algorithm that I use, or that I'm proposing to test whether something is connected or not, which can probably be written in terms of this language here, but I won't do it, is that if you have, and this is how eventually we'll see, hopefully we'll see questions, if you want to say that something is disconnected, all you're going to do is you're going to name two vertices and say that there's no series of edges between the two of them. That's enough to say it's disconnected. To say it's connected, what you can do is you can describe a walk, which is a series of edges that includes all vertices. So for example, taking graph 2 here, and let's name them, I'm going to call V, well, I'll just call them 1, 2, 3, 4, 5, 6. So I can say that G2 is connected as there is a walk containing all vertices. And the question is, why does this mean that it's connected? Well, we'll answer that in a second. So you can walk from 1 to 2 to 3 to 4 to 5 to 6. So that's a walk containing all vertices, or all nodes. 1 to 2 to 3 to 4 to 5 to 6. So this proves that it is connected, because to be connected there has to be a series of edges between any two nodes. So you can pick any two nodes here, and there's, I don't know how many, there's 15 ways of doing that. However you do it, say if it's 2 and 5, just pluck out that part of the walk containing all the vertices, and that is a series of edges from 2 to 5. So just imagine it like it's going to be connected if you can walk around and hit every single vertex, which you can't do here. Now maybe you can kind of come up with an algorithm like that. I'm going to just tell you how I propose you do it. Okay, so the first thing is that if the thing about a walk is you can go back on yourself. So like you could, if you want, start and end it, well, you could start at 2 anyway. So like to make this into a walk starting at 2, just start at 2, go back to 1, then go back to 2, go to 3, to 4, to 5, to 6. So you can always start wherever you want in this in this walk or something like that. Okay, anyway, let me just write down what I consider an algorithm. So take a vertex or node at random. Okay, now you can do this using these things. So say for example you picked V1 in this picture here. What I want you to do now is list V1 and all the vertices that are a distance 1 away from V1. And you can do that here. So just list V1 and all the vertices that are in a 2-element set with this. So if you list V1 and all the things that are in a set with V1, you get V1, we said that. You also get V2 and you get V3. So that's how this could work on this. So let's take a vertex at random, we'll call it, we'll call it V0. So list V0 and all vertices at distance 1. Now what I mean by distance of 1, I mean there's one edge between the starting, what I'm calling V0, and it. So if you're doing it on graph 1, you'd get V1, you get V2, you get V3. And all verts at distance 1 from V0. call this big V1. Okay. Then list all elements of V1 and all elements a distance 1 from them. So we'll probably have to explain this, and we'll do it maybe on this graph here. Okay, so call this list V2. Okay, now repeat. So now you learn about loops. So basically repeat. So now you'll list all of V2 and all the elements of distance 1 from those elements and call that V3. So repeat for V3, V4, and you keep on going until you get 2 of them are the same twice in a row. And if this Vk, which is basically all the vertices you can get to from V0, is equal to all the vertices, then the graph is connected. Else disconnected. So we'll run this algorithm. Now this by the way is just a learning task. It's just kind of get you understanding what connected is. We're not going to ask you to write algorithms or anything like it. So we're going to run it on these two here. Run this algorithm. So we'll call this graph 3 and we'll call this graph 4 and we'll just label the vertices 1, 2, 3, 4, 5, 6, 7. And we'll label the vertices here 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's do it. I'm going to take a sheet of paper. Now, this isn't something to be written in because this is just a learning task that you look at. Now, if you want to try it yourself, on Saturday I'm going to scan, I've got a sheet with loads of different graphs that you can try these things on. Right, so let's look at graph 3. Now let's take our vertex at random is V0. V0 is equal to 1. So let's see. Okay, so graph 3. Is it connected or not? So take the very first set we'll call the vertex now. It's V0 in the algorithm. Oh, where's that written? It's called V0, but we're just going to call it the set. We're going to call the set V0 and we're going to call the starting vertex 1. Okay, so now what does it say? List this element, which would be 1, and all the vertices at distance 1 from 1. And we'll call this V1. So V1 consists of, so you take 1. Now let's see everything that's a distance 1 from 1. So I got 2, 3, 5, 4. See that? 2, 3, 5, 4. 2, 3, 5, 4. Now what you do is you go again, list all the elements of V1, which is 1, 2, 3, 5, 4. And then all the elements, now it's a set, now it says list, I kind of mean a set there. All the things that are 1 away from 1, 1 away from 2, 1 away from 3, 1 away from 5, 1 away from 4, but I don't repeat myself. So in particular, there's no point writing 1 again, or there's no point looking at 1 because all of them are there. Now let's look at 2. What's the distance 1 away from 2? I see 1, 3, and 7. And by the way, this can all be done in this kind of language here, but we don't have to do that. So 1, 3, and 7. I've already got 1 and 3, so I'm just going to put in 7. Okay. And now what about 3? What's 1 away from 3? I see 1, 6, and 4. I've already got 1 and 4, so I'm just going to do 6. What about 5? So 5, I see 1, 3, 4, 7. I've got 1, 3, and 4, so I'll just put in 7, but in fact I've already got 7. And then finally I just have to look at 4. What's 1 away? 1, 3, 5, and 7. I've got all of those already. So now I do it again. Now, everything from 1 to 4 I've already done, so I just write them down and I don't worry anymore. Now I look at everything that's a distance 1 from 7. I see 6, 2, 5, 4, but they're all already there. 6, 2, 5, 4. Actually, I'm supposed to write in 7 and 6. Yeah. So I don't have to go through 1 to 4. So 7, 6, everything I mentioned was already there. And look at 6, 3, and 7. They're already there. And now notice that these two are the same. So I stop. And I ask, is this equal to the vertex set? So the vertex set of graph 3 is the set containing 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Are these the same set? Yeah, both of them have 1, both of them 2, both of them 3, both of them 4, both of them 5, both 6, both 7. And because these two are the same, that means that G3 is connected. And maybe for an exercise for yourself to see can you understand this, you might try and do it yourself on this and see what happens. What should happen is you get down, you get the same two things. Oh, sorry, this should be V2, this should be V3. You get the two things twice in a row, but it doesn't give you all the vertices. And that, if you think about it, means that it's not connected. Right. So let's plow on a little further. So that's connectedness. So it's should be pretty obvious. So degree. So we already met the concept of degree when looking for a trail through an undirected graph that uses all the edges. Apart from the starting and ending nodes, each node must have an even number of edges for such a route to exist. This number of edges is the degree of each node. So say if I draw a graph here and I want to name the nodes, let's call them 1, 2, 3, 4, 5. Let's draw some edges. Okay, now we need to think about the loops for a second. The loops will count as 2 edges. Is that right? Loops count twice. I haven't got a very good reason for you, but things don't work. Yeah, you have to include them as counting twice. So we have the following things. So the way now, what I don't want to see is like. So let's write down the degrees here. So this has got 1, 2, 3, 4. 1, 2, 3. 1, 2, 1, 2, 1, 2, 3. Now what I don't want to see is stuff like 1 is equal to 4. That's very, very bad maths. What's equals for is to say the two things are the same. So to do it properly, what you would do is as follows. You'd write that the degree of 1 is equal to 4. You'd write the degree of 2 is equal to 3. The degree of 3 is equal to 2, and it's the number of edges that hit it. 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 1, 2, 3, 4. The degree of 3 is equal to 2. The degree of 4 is equal to 3, and the degree of 5 is equal to 2. Now, if you want to write that another way, I do not want, if you write 1 is equal to 4, I'm going to mark it down. That's just not good maths. Alternatively, how about something like this? Vertex degree. So vertex 1, 2, 3, 4, 5. So you could do it with a table. Degrees 4, 3, 2, 3, 2. Now, there's a thing written down here that it's a function, but as we mentioned, I've changed the order of the notes, so this isn't possible anymore. I'll just write down what it is. So it's just another way of writing it. So there's, you can do it as a relation between V and N0. And you include the 0 because you could have a node with no edges on it. It would have a degree of 0. So another way of writing is with ordered pairs. We'll see this a little later. So like 1 is related to 4. So it's like it's a relation between a vertex and its degree. 2 is related to 3. 3 is related to 2. 4 is related to 3. And 5 is related to, and you can say it's like it's a relation called degree. set of ordered pairs. So you can do this, you can do this, you can do this. If you write 1 is equal to 4, 2 is equal to 3, 3 is equal to 2, 4 is equal to 3, 5 is equal to 2, I'm going to mark you down. Now the other thing we set up here, there's this trail through the graph that uses every edge, if and only if there's 2 nodes of odd degree or no nodes of odd degree. So actually we should be able to do it here. So we just play around. We know that we have to start and end at 2 and 4 at the nodes of odd degree. So start here, end here, let's go. So if we go here, we can't go back, so we have to do the loop first. So this is this Euler trail. So do a loop from 2 to 2, then go to 3, then go to 4. Now, I think it doesn't matter whether you go to 1 and do a loop and go to 5 and back, or else do it the other way around. It doesn't really matter. Let's go from 4 to 5. Let's go from 5 to 1. Let's do a loop to 1, and then we go to 4. And if you look at this, it uses every single edge. It uses this edge. I'm just going to draw it. It uses this edge to do the loop. 2 to 3 uses this edge. 3 to 4 uses this edge. 4 to 5 uses this edge. 5 to 1 uses this. 1 to 1 uses this loop. And 1 to 4 uses this. And this is called, we may as well introduce the language again. This is an Euler trail. If it starts and ends at the same node, we call it an Euler circuit. Okay. So yeah, we said here loops are counted as double edges, so that the degree of node A below is 3. So we might just to fill in this bit, A, B, loop, edge. So just to be clear, just so we get the notation right, you can use degree of A is equal to 1, 2, 3. You can write degree of B. What's the degree of B? 1. Or you can use this ordered pair notation. The degree of A is equal to 3. The degree of B is equal to 1, and it's a relation. Or you can do a little table. So vertex degree, vertex A, vertex B. Vertex A has degree 3, vertex B is degree 1. Either of these are just 3 different ways of writing the same thing. Okay. Now we should have time for this last thing. So this is another collaborative task. So go into a group of size greater than 3. Now let's let's make the group so red, blue, green, orange. 4 people: Mr. Red, Mrs. Blue, Mr. Green, Mr. Orange, whatever. So each person in the group is a node, so that V is the set of people in the group. So V is red, blue, green, orange. Draw the nodes below using a letter or letters to denote each person. So let's say red, blue, green, orange. So this is to be done, it's a group thing, so obviously you can't do it. Red, blue, green, orange. Now some people in the group are to shake each other's hands. Definitely couldn't do this. Okay, so let's have some shakes. Let's have red shaking green, green shaking blue, red shaking blue, and finally orange shaking blue, something like this. Every time 2 people shake hands, draw an edge between them. Yeah, so that's some of the people who shook hands. Calculate for this graph the degree of the nodes. So I'm going to write the degree of B is equal 1, 2, 3. The degree of orange is equal to 1. Degree of green is equal to 2. And finally, the degree of red is equal to 2. Now this also, by the way, has an Euler trail because there's 2 nodes of odd degree, and it's easy enough to see orange to blue to green to red to blue. Add up the degrees and make an observation about the answer. So I'm going to just do a little bit of notation for you that you might see at a later date. So we could say something like this means add up, and let's write V in adding up over the vertex set, adding up over red, blue, green, orange, the degree of the vertexes. So you do what's red, the degree of red is 2, plus the degree of blue is 3, plus the degree of green is 2, plus the degree of orange is 1. So you get 2 plus 3, 5, plus 2, 7, plus 1 is 8. And the idea is to make some observation. And the only thing that really everyone in the class, if they did it, would see is that this is even. So if you add up the degrees, you get an even number. Now we might explain why that's always the case on the next page. And then the next thing is count up the number of nodes of odd degree. So for this is question 6, or part 6, and part 7. How many nodes of odd degree? There's 2. 2 nodes of odd degree. Okay, I don't have that much time left in the lecture, so we'll see how we go. So, let us explain. So, 2 nodes, make an observation. The number of nodes of odd degree is also going to be even. Now, let's explain this quickly. If we add up the degrees, what happens is, if you look at this edge, it gets counted once here and once here. If you look at this edge, it gets counted once here, once here. This edge counted once, and this edge counted once. So what that means is if you add up the degrees, you get twice the number of edges. So the sum of the degrees is equal to twice, and how will I get to say the number of edges? Well, the edges is a set, and if I put bars around it, it says the number. So add up the degrees is twice the number of edges. That has to be even. And then the other one is a bit weirder. I'll let you think about it. So suppose you had, so you got even degrees and odd degrees. So suppose you had an even number plus an even number plus an even number. And this is certainly even. And then some odd numbers. So say the first odd number and a second odd number. What happens when you add up 2 odd numbers? You get an even number. So even numbers plus an even number of odd numbers, be even plus even is even. And what's not possible, and my time is very short here, is to have an odd number of nodes of odd degree, because this is supposed to be adding up the degrees. So add up the degrees. So this just says add up the degrees, and suppose the degrees are even, and 3 odds. That's not possible, because 3 even numbers and 3 odd numbers, well, these make up even, and even plus odd is odd. So there must be, that's not possible, because this has to be an even number. So the number of nodes of odd degree is even. So we'll go very quickly on this, the handshaking lemma. In undirected graph, the sum of the degrees is even. The sum of the degrees is equal to twice the number of edges, and the number of nodes of odd degree is